Welcome to this problem walkthrough. Today, we're tackling problem number 1253, reconstruct a two-row binary matrix. In this session, we'll explore the problem, break down the solution step by step, and analyze different approaches to solve it. Let's dive in. In this problem, you are tasked with reconstructing a two-row binary matrix based on specific constraints. The inputs provided are two integers, upper and lower, which represent the sum of all the values in the first and second rows of the matrix, respectively. Additionally, you are given an array called colsum, where each element determines the sum of values in the corresponding column of the matrix. Your goal is to construct a valid binary matrix where each element is either 0 or 1. The matrix must meet three main criteria. First, the total of the first row should equal upper. Second, the total of the second row should equal lower. And third, for every column, the sum of the two rows in that column must equal the corresponding value in colsum. If it's not possible to construct such a matrix, you need to return an empty list. This problem tests your ability to carefully distribute values across rows and columns to meet these precise conditions. The output for this problem is a 2D integer array of size 2xn, where each element is either 0 or 1, and the matrix satisfies all the conditions outlined earlier. If no such matrix can be constructed, you must return an empty list. Let's consider an example to understand this better. Suppose the inputs are upper equals 2, lower equals 1, and colsum equals 1, 1, 1. A valid output would be the matrix 1, 1, 0, 0, 0, 1. Here, the first row sums to 2, the second row sums to 1, and the column sums, which are 1, 1, and 1, match the given colsum. This demonstrates how the solution satisfies all the constraints provided. To build on this concept, let's look at another example. If the inputs are upper equals 2, lower equals 3, and colsum equals 2, 2, 1, 1, it becomes impossible to construct a valid matrix. The reason is that the total sum of upper and lower is 5, but the sum of colsum is 6. This mismatch in sums makes it mathematically impossible to allocate values across the rows and columns to satisfy all the constraints. As a result, the output in this case would be an empty list. This highlights the importance of ensuring that the sum of colsum matches the combined values of upper and lower, as it's a prerequisite for solving the problem. Now, consider another example where a valid matrix can be constructed. If the inputs are upper equals 5, lower equals 5, and colsum equals 2, 2, 2, 1, 1, 0, one possible solution is the matrix 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0. Here, the first row sums to 5, and the second row also sums to 5, which matches the given upper and lower values. Additionally, the column sums 2, 2, 2, 1, 1, and 0 align perfectly with the provided colsum. This example showcases how a valid matrix can be constructed if all the conditions are met, and it also emphasizes the flexibility in distributing values across rows while adhering to the constraints. Finally, it's important to understand the rules for interpreting the colsum values and their implications for constructing the matrix. If colsum I equals 0, it means both rows in column I must be 0. If colsum I equals 1, exactly one row in column I must have a 1, and the other row must have a 0. If colsum I equals 2, both rows in column I must have a 1. Additionally, the solution needs to be efficient, as the length of colsum can go up to 10,000. Edge cases to consider include scenarios where upper or lower is 0, where colsum contains only zeros or only 2s, or when the total sum of colsum does not match upper plus lower. These edge cases help ensure your solution is robust and handles all possible inputs correctly. To tackle this problem, we initially considered a brute force approach. The idea here is to generate all possible two-row binary matrices of size n, where n corresponds to the length of the colsum array. For each generated matrix, we would check if it satisfies the constraints given by upper, lower, and colsum. However, some important observations can help us limit our search space. For example, if colsum I is 0, both rows in column I must be 0. If colsum I equals 2, both rows must be 1 in that column. And if colsum I equals 1, exactly one of the rows must be 1. While these rules help reduce the search space, the brute force approach is still computationally impractical because generating all possible two-row matrices grows exponentially with the size of n. Specifically, the time complexity of this method is O(2)(2n), which makes it infeasible for larger inputs. Therefore, despite its simplicity, we avoid this approach due to its inefficiency and lack of optimization for the problem structure. A more efficient and practical solution is the greedy approach, which constructs the matrix column by column based on the values in the colsum array. The logic is straightforward. If colsum I equals 2, both rows must have a 1 in column I, and we reduce both upper and lower by 1. If colsum I equals 1, we assign a 1 to the row corresponding to the larger remaining value, either upper or lower, and decrement the chosen value accordingly. Lastly, if colsum I equals 0, both rows in that column get a 0 with no changes to upper or lower. This greedy strategy ensures that at each step, we make the optimal choice while respecting the constraints. By iterating through the colsum array once, we achieve a time complexity of O(n). Additionally, the space complexity is O(n) to store the resulting matrix. This approach was chosen because it efficiently constructs the solution while ensuring correctness, avoiding the exhaustive explorations required in brute force. Another approach we considered was backtracking, which is a common strategy for constraint satisfaction problems. Here, we would recursively explore all valid assignments for the matrix, starting with an empty configuration and placing zeros or ones in each cell while ensuring the constraints imposed by upper, lower, and colsum are met. This method is powerful in situations where constraints need to be dynamically enforced, but in this problem, the constraints can be resolved incrementally in a greedy fashion. The backtracking approach has a worst-case time complexity of O(2 to the power of n), as it explores all potential combinations, making it slower than the greedy method. Given that the greedy approach is both simpler and more efficient, backtracking is unnecessary here. As a result, we chose the greedy strategy because it avoids the overhead of exploring unnecessary possibilities and directly constructs the solution in a straightforward manner. The greedy approach provides the best balance between efficiency and clarity for solving this problem. By iterating through the colsum array and making optimal decisions for each column, we construct the solution while enforcing the constraints on upper and lower step by step. This method offers a linear time complexity of O(n) and a space complexity of O(n), making it highly efficient. However, it's worth noting that careful implementation is required to handle edge cases, such as scenarios where no valid solution exists. Despite this, the greedy approach stands out as the optimal strategy because it leverages the structure of the problem to avoid unnecessary computations. Its combination of speed, simplicity, and correctness makes it the ideal choice for reconstructing this two-row binary matrix. To reconstruct a two-row binary matrix, we first need to understand the problem and its constraints. You are given three inputs, upper, lower, and an array colsum. The task is to construct a binary matrix with two rows and in columns such that the sum of the first row equals upper, the sum of the second row equals lower, and for each column I, the sum of both rows equals colsum I. If it's not possible to construct such a matrix, we must return an empty matrix. Now, let's break this down. Each column in the matrix can only have specific combinations of row values, 0, 0, 1, 0, 0, 1, or 1, 1. The value of colsum I determines which combinations are valid. For example, if colsum I is 0, the column must be 0, 0. If it's 1, the column can be either 1, 0, or 0, 1. And if colsum I is 2, the column must be 1, 1. Additionally, the total number of 1s in the first row must equal upper, and the total number of 1s in the second row must equal lower. These observations form the foundation of our approach. To start solving the problem, we first need to validate the input. Specifically, the sum of colsum must match upper plus lower. This is because the total number of 1s in the entire matrix is fixed by these constraints. If this condition isn't met, we can immediately return an empty matrix since it's impossible to construct a valid solution. Once the input is validated, we initialize the result matrix. This is a 2D list with 2 rows and n columns, where all values are initially set to 0. Then, we iterate through each column of colsum. When colsum I equals 2, we assign 1 to both rows in that column, i.e., matrix 0 I equals 1 and matrix 1 I equals 1. We then decrement both upper and lower by 1, as we've allocated 1 1 to each row. If colsum I equals 1, we prioritize the row with the larger remaining quota of 1s. If upper is greater than lower, we assign matrix 0, I, equals 1 in decrement upper. Otherwise, we assign matrix 1, I, equals 1 in decrement lower. Finally, if colsum I equals 0, the column remains 0, 0, and no changes are made. This iterative process helps construct the matrix step by step while maintaining the constraints. After processing all columns, we need to verify the final constraints. Specifically, we check if both upper and lower have been reduced to 0. This ensures that the required number of 1s has been placed in each row. If either upper or lower is not 0, it means the constraints couldn't be satisfied, and we return an empty matrix. However, if all constraints are met, we return the constructed matrix as the final result. There are some key insights that make this approach effective. First, the sum of colsum must equal upper plus lower because the total number of 1s across both rows is fixed. Second, the greedy assignment strategy ensures that when colsum I equals 1, we prioritize the row with the larger remaining quota of 1s. This minimizes the risk of running out of slots in one row before all constraints are met. Lastly, if at any point during the process upper or lower becomes negative, we can terminate early since it's impossible to construct a valid matrix. To implement this solution efficiently, we use a 2D list to represent the matrix. This allows for quick assignment and retrieval of values as we iterate through colsum. We also maintain two integer counters, upper and lower, to track the remaining number of 1s that need to be placed in each row. In terms of complexity, the time complexity is O, n, where n is the length of colsum, as we process each column in constant time. The space complexity is also O, n, due to the storage required for the result matrix. Lastly, there are a few edge cases to consider. If the sum of colsum doesn't match upper plus lower, the input is invalid, and we return an empty matrix. If colsum contains values other than 0, 1, or 2, the input is also invalid. Additionally, if at any point the constraints cannot be satisfied, such as when upper or lower becomes negative, we terminate early and return an empty matrix. These considerations ensure that our solution is both robust and efficient. Here, we define our solution class and the method Reconstruct matrix, which takes three inputs, upper, lower, and colsum. The upper and lower values represent the maximum number of ones we can assign to the first and second rows, respectively, while colsum is a list indicating the sum of each column. We start by determining the length of colsum and initializing a 2D result matrix with zeros. This matrix will eventually hold our reconstructed binary matrix. Next, we iterate over each column in colsum. If a column sum is 2, it means both rows must have a 1 in that column. In this case, we check if both upper and lower are greater than 0, which ensures we have enough quota to assign these ones. If so, we assign ones to both rows, decrement upper and lower, and move to the next column. If not, it's impossible to satisfy the conditions, so we return an empty list to indicate failure. If the column sum is 1, only one row gets a 1. Here, we prioritize the row with the higher remaining quota. If upper is greater than lower and positive, we assign the 1 to the first row in decrement upper. Otherwise, if lower is greater or equal to upper and positive, we assign the 1 to the second row in decrement lower. If neither condition is met, meaning we lack sufficient quota, we return an empty list to indicate that reconstruction isn't feasible. Once the loop has completed, we perform a final check to ensure that both upper and lower quotas have been fully utilized. If both values are 0, it means the reconstruction was successful, and we return the result matrix. However, if either upper or lower remains greater than 0, it means the conditions were not met, and we return an empty list to signify failure. This final step ensures the solution adheres strictly to the constraints provided in the problem. Here, we start by importing the necessary libraries and defining our solution class. The method Reconstruct matrix takes three inputs, upper, lower, and colsum. Upper and lower represent the number of ones we can assign to the first and second rows, respectively, and colsum is the list of column sums for the binary matrix we need to construct. First, we determine the number of columns, n, based on the size of colsum, and initialize an empty result matrix with two rows, each filled with zeros. This is done using a loop and the collections.nCopies method. Next, we iterate through each column in colsum. If the column sum is 2, it means both rows must have a 1 in that column. We check if upper and lower are greater than 0, and if they are, we assign 1 to both rows at the current column, decrementing upper and lower accordingly. However, if we don't have enough quota to satisfy this condition, we immediately return an empty list since it's impossible to construct the matrix in such a case. Now, for columns where the sum is 1, we need to decide which row gets a 1. If the upper quota is greater than lower and still positive, we assign a 1 to the first row and decrement upper. Otherwise, if lower is greater than or equal to upper and still positive, we assign a 1 to the second row and decrement lower. If neither condition is met, meaning there's insufficient quota to allocate a 1 to any row, we return an empty list. Finally, after processing all columns, we check if both upper and lower have been reduced to 0. If they have, we return the constructed result matrix. However, if there is any mismatch in the remaining quotas, we return an empty list, as it's not possible to satisfy the constraints with the given inputs. In this example, we start with the input values, upper is 2, lower is 3, and colsum is 2, 2, 1, 1, 0. First, we initialize the variables. The length of colsum, n, is 5, and we create a 2x5 matrix called result, filled with zeros. Now, we process the first column, where colsum, 0, equals 2. Since colsum, I, is 2, both rows need a 1 in this column. Because upper and lower are both greater than 0, we assign result, 0, 0, to 1 and result, 1, 0, to 1, then decrement upper and lower by 1. This gives us updated values of upper equals 1 and lower equals 2. The intermediate result matrix is now 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Next, we process colsum, 1, which is also 2. Again, both rows need a 1. Since upper and lower are still positive, we assign result, 0, 1, to 1 and result, 1, 1, to 1, then update upper to 0 and lower to 1. The intermediate result matrix becomes 1, 1, 0, 0, 0, 1, 1, 0, 0, 0. Now we move to colsum, 2, which equals 1. Here, only one row can get a 1. Since upper is 0 but lower is greater than 0, we place the 1 in the lower row, setting result, 1, 2, to 1, and reduce lower to 0. The updated matrix is 1, 1, 0, 0, 0, 1, 1, 1, 0, 0. For colsum, 3, which is also 1, there is no quota left in either upper or lower, so this column remains unchanged. The intermediate result stays as 1, 1, 0, 0, 0, 1, 1, 1, 0, 0. Finally, we process colsum, 4, which is 0. Since colsum, I, is 0, both rows must remain 0 for this column. This means the result matrix is finalized as 1, 1, 0, 0, 0, 1, 1, 1, 0, 0. The output for this example is therefore 1, 1, 0, 0, 0, 1, 1, 1, 0, 0. Now, let's consider another scenario. In this second example, the input values are upper equals 2, lower equals 1, and colsum is 2, 2, 1. First, we initialize n as 3 and create a 2x3 result matrix filled with zeros. We begin by processing colsum, 0, which is 2. Just like before, both rows need a 1. Since upper and lower are both positive, we assign result, 0, 0, to 1 and result, 1, 0, to 1, then decrease upper to 1 and lower to 0. The intermediate matrix is now 1, 0, 0, 1, 0, 0. However, when we move to colsum, 1, which is also 2, we encounter a problem. Both rows would need a 1 again, but lower is already 0. This means it is impossible to satisfy colsum, 1, so we immediately return an empty array. The output for this example is therefore an empty matrix, represented as. Now let's examine an edge case where all the input values are 0. Here, upper is 0, lower is 0, and colsum is 0, 0, 0. As usual, we initialize n as 3 and create a 2x3 matrix filled with zeros. For each column, colsum, I, is 0, meaning both rows must remain 0 for all columns. No updates are needed, so the matrix stays as 0, 0, 0, 0, 0, 0. The final result is 0, 0, 0, 0, 0, 0. This demonstrates that when all inputs are 0, the output is simply a matrix of zeros. The time complexity of the solution is determined by evaluating the main operations performed by the algorithm. First, during initialization, we create a 2-row by in-column matrix filled with zeros. This step takes n time because we need to allocate space for n elements in each row, and there are 2 rows. Next, the main for loop iterates over the callsum array. For each element, we perform a series of constant time operations, such as comparisons and assignments. Since there are n elements in callsum, this loop also takes n time. Lastly, there's a final quota check to ensure both upper and lower are 0 after the loop. This is a simple constant time operation, taking 1. Since the loop dominates the overall runtime, the total time complexity is n. The space complexity of the solution is driven by the memory used to store the result matrix. This matrix has 2 rows and n columns, which results in a space requirement of 2 n, or simply n. The input variables upper, lower, and callsum do not contribute to the space complexity because they are provided as input and not created within the function. Beyond the result matrix, we use a few auxiliary variables, such as integers for indexing and bookkeeping, which require only 1 space. Therefore, the overall space complexity is dominated by the result matrix, leading to a total of n. To understand the time complexity more deeply, we can analyze the best, average, and worst cases. In the best case, the function exits early during the first loop due to invalid conditions, such as when the upper or lower quotas are not satisfiable. Here, the time complexity is 1, because the function returns almost immediately. In the average case, the function processes all n elements in the callsum array, performing operations for each element, resulting in n time. Similarly, the worst case occurs when the function iterates through all n elements without exiting early, leading to the same n complexity. Comparing this to a brute force approach, which would involve generating and checking all possible 2xn binary matrices, the brute force method would take 2n time. This exponential complexity is vastly less efficient than the current linear solution, which is n. To mathematically validate the big O analysis, let's revisit the main operations. The loop over the callsum array processes each element exactly once, performing constant time operations for comparisons and updates. With n elements in the array, this results in a time complexity of n. For space complexity, the memory usage is dominated by the result matrix, which contains 2 rows and n columns. This requires 2 n space, which simplifies to n. These findings confirm that the algorithm is linear in both time and space, making it an efficient and scalable solution for handling large inputs. One of the most common mistakes is not properly handling edge cases. For example, if the callsum array consists entirely of zeros or ones, some solutions fail to return a valid matrix or perform unnecessary computations. This happens because edge cases often represent boundary conditions that can break your algorithm if they're not explicitly addressed. Another frequent issue is misunderstanding the constraints on the rows. For instance, some solutions mistakenly allow column values greater than 2 in a binary matrix, which violates the problem's rules. Any solution that doesn't respect these constraints will produce invalid results. Finally, using a brute force approach to generate all possible matrices and testing each one is another mistake to avoid. This method quickly becomes computationally infeasible as the input size increases, since the number of potential matrices grows exponentially with n. A more efficient strategy is necessary for larger problems. Another important point is validating the input. Some solutions assume that the sum of callsum is always achievable with the row sum limits, but that's not guaranteed. For example, if the total sum of callsum exceeds the available slots in the 2 rows, the input becomes invalid. Without proper validation, your algorithm could enter infinite loops or return incorrect results. Another pitfall is hard-coding solutions for small inputs, such as writing special case code for n equals 2 or n equals 3. While this might work for specific cases, it doesn't scale to larger inputs and can lead to bugs if constraints change. A robust, general approach is always better in the long run. To succeed in interviews, it's essential to fully understand the problem statement. Carefully consider the constraints on both the callsum and the rows, and don't hesitate to ask clarifying questions to confirm edge cases. Before implementing a solution, focus on feasibility, check whether the problem setup even allows for a valid solution. For instance, if the sum of colsum exceeds the limit imposed by the row sums, no valid matrix can be constructed. Also, prioritize readability when writing your code. A greedy approach is often preferred because it balances efficiency and clarity, and it demonstrates your ability to choose appropriate algorithms. Finally, be ready to discuss trade-offs. For example, you might explain why you chose a greedy solution instead of a dynamic programming approach, emphasizing the balance between scalability and simplicity. Additionally, reviewing related problems like partitioning arrays or matrix operations can deepen your understanding and help you recognize patterns in similar challenges. There are several alternative approaches to solving this problem. The greedy approach is one of the most efficient. It works by iterating through the colsum and assigning values to the matrix columns based on the column values, such as assigning to both rows when colsum I equals 2. While efficient with a time complexity of O(n), this approach requires careful implementation to ensure all constraints are satisfied. Another option is backtracking, where recursion is used to explore all possible matrices while pruning invalid configurations. This method is more flexible but significantly less efficient, with a complexity of O(2 to the power of n), making it impractical for larger inputs. Finally, dynamic programming offers a state-based approach to dynamically calculate feasible solutions column by column. While this can handle more complex variations of the problem, it's often overkill for the simpler constraints in this particular challenge. Choosing the right approach depends on the specific requirements and constraints of the problem you're solving. Great job following along. In this problem, we reconstructed a two-row binary matrix efficiently while considering constraints. Remember, tackling edge cases and optimizing your solution are essential skills for interviews. Thanks for watching, and don't forget to like and subscribe for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!